Hello, my name is Larry Kelley. I'm the founder of ICT Corporation. I started ICT back in 1969, and I'm the owner of the company. We make many different types of crystals. We make ruby, sapphire, garnet, cubic zirconia, various laser crystals. I think that we make more types of actual crystals than any other company on the planet. We've invented a new, simple method of making very thin, very inexpensive silicon solar cells. We're positioned to become a major player in the large alternative energy market. We have a team of very skilled and knowledgeable people. All of us have had many years of design and management experience. We've designed and built all of the furnaces and control equipment that we use daily in our crystal factory. The furnaces operate at temperatures up to 5,000 degrees, and they have to be controlled very, very, very carefully. Ruby forms at over 3,700 degrees, and cubic zirconia forms around 5,100. By the way, we're the company that actually figured out the commercial way to make cubic zirconia back about 20 years ago. Silicon, what we'll be talking about today, silicon forms at a comparatively low temperature of only 2,600. That's very easy for us to work with. It's lower than any of the other crystals that we make. Just to let you know how what we do, we've built turnkey crystal growth factories in Thailand. We built them in India. We built one in France. We built one in California. We used to operate 2 companies in mainland China that employed about 150 people. This might be a good time to talk about what we want to do now. We've got 3 goals. Our first goal is to make the world's least expensive solar cell. Now, when you talk about solar cells, everybody talks about a 1-watt cell. That's a cell that will put out 1 watt of electricity when it's exposed to the sun at noon. We think we can easily produce a 1-watt cell for under 30 cents. When we wire a number of the cells together into an array, we think we can make the array for under 50 cents per watt. Presently, First Solar has the lowest reported cost of 84 cents per watt in an array configuration. Our second goal is to produce a high efficiency cell of around 18%. This really should be quite easy with our process. A higher efficiency cell takes less space to deploy, and that means less support structure and less roof or land area. And our third goal is to design very inexpensive and durable equipment which to make the cells. We want a capex of less than 40 cents per watt, and which is far, far less than any competing process. It's good to understand the actual cost of an individual solar cell and an array of cells. There are 7 major cost centers in making an array. You can see them all listed here, along with the cost of each step. These costs have been carefully tabulated, and they're really quite conservative. We think our cells will cost about 24 cents a watt. We can make a complete weatherproof array for around 45 cents per watt. Now, First Solar reports a cost per watt of 84 cents, but that's only if they make their cells in Singapore, which has low labor costs. We plan on making our cells right here in Michigan. Here are some of the major players in our industry. You might notice that only 3 companies here actually make a cell that's more efficient than 16%. All 3 of these companies do use silicon crystals just like we'll be using, but as you'll see later, their costs are very, very high. The market today is made primarily up of companies that are using some form of silicon, about 86% actually. In the long run, I think about 99% will be using silicon, mainly just because there's a lot of silicon on the planet. There's a lot of sand on the planet. Sand is basically a silicon dioxide. If you take away the oxygen, all that remains is silicon. it's abundant, and it's not cancer causing. The reason I mention that is because that company First Solar that I've been mentioning, they make their cells out of cadmium telluride. That's the CDTE you see here. Now cadmium is it's a dangerous material. It's regulated. It causes cancer. We don't plan on using any of that. The worldwide push is to get the cost of arrays down to less than $1 a watt. That's with a low capex. So far, only First Solar has proven able to do that. Now, NanoSolar says they can, but they haven't released any figures. All the other companies are stuck with costs of far over $1 and no practical path to lower costs. The thin film processes, the cadmium telluride and the cadmium, the SIGs, have two limitations, which I think is going to prove fatal to those companies in the long term. First of all, their efficiencies are limited to 11 or 12%, and they don't make individual cells. They make whole big arrays or whole big panel at once, and they have to divide them up. And I'll show you later on why that's it's not a good idea to do that. This slide and the next two slides show the reasons why all the present methods of making solar cells are expensive. Here we can see why companies making cells from either single crystals or from cast blocks have such high costs. They've got very slow, energy-intensive formation of the crystals that they need. Also, what I call squaring losses on the cylindrical crystals are nearly 40%. Both materials, the cast and the grown crystals, need to be sawn into wafers. And due to the nature of silicon and the thickness of the saw blades or the saw wires, there's another 50% loss of silicon just in sawdust. Plus, there's additional labor is needed to smooth out the saw damage. This is just a rehash of the previous slide with the addition of another way of obtaining wafers of silicon. Evergreen Corporation grows what they call ribbons of silicon. This is an incredibly expensive method of crystal growth. The heat energy losses are very high per gram of silicon. We tried this 30 years ago and we found out that it's more expensive than slicing the silicon. I mean, here's a close-up photo that's been released by Evergreen. You can see the crystal ribbon is very, very bumpy and uneven, and they report some of the highest silicon costs I've ever seen. They're a public company. I mean, you can download all their financials. They're losing money. They've lost about $69 million just in the last quarter of last year. I just, honestly, I can't understand why anybody invests money in that company. Well, what about China? Well, it's always a little bit of a worry, but they're using standard technology and their costs are rising quickly. We used to own and operate two companies in China. We're really quite familiar with the costs there. The Chinese government says that they're going to be raising their minimum pay by 21% in the next couple of months. And so we're really not too worried about the factories there. We've made sure that our design for making cells is not labor or capital intensive. We'll have a very, very strong patent portfolio which will help protect our technology. We also believe in trade secrets. I'm not really worried about China at all. We believe the best plan is to develop a disruptive technology, which we have. It's less expensive and simpler than any other. We plan on catching everybody by surprise. We want to operate in stealth mode until we start selling panels. We just plan on keeping it simple. This is a little more information for you to digest. Basically, we use silicon because there will never be a shortage of it. We use as little as possible because even though there is a lot of it around, it's expensive to refine it to the purity needed for solar cells. By using a tiny amount, we can crystallize it faster than any other company. Crystallized silicon solar cells are highly efficient. They're about double the efficiency of the thin film or the SIGs or the cadmium telluride cells. And by making the whole process simple, we keep our capex very, very low. This is just to drive home the importance of using very thin silicon. It's all a matter of dollars and cents and common sense. 3 cents worth of silicon in our process versus 36 to 48 cents of silicon per watt in competing processes. This is a really important slide. It tells you why making individual cells are better than making cells in rolls or in sheets. I mean, you see all this publicity pictures of solar cells coming in rolls or large sheets. That's all smoke and mirrors, as far as I'm concerned at least. I mean, it's true that if you use a thin enough layer of silicon or SIGs, you can manufacture cells pretty quickly, but the thin coating is never perfectly even. And due to the electrical nature of solar cells, these sheets have to be divided into smaller individual cells anyhow. I mean, please study this slide carefully later on at your leisure. I'll just take my word for it that individual cells are much better than rolls or sheet cells. Also, efficiency is really, really important. Every thin film cell made has a lower efficiency than any crystalline silicon cell, generally about half the efficiency. That means double the mounting cost, double the land area, it's double the wiring cost, double the labor. I mean, it's very, very, very important. This is just sort of an introduction to the next slide, which is actually going to be a movie. What you'll see next is the first publicly released view. Well, it's not really publicly released, we're releasing it to you, but it's the first released view of our overall process. It uses centrifugal force to spread a thin layer of silicon onto a conductive substrate. No one else in the world does this. It was invented and patented by me, by ICT Corporation. This centrifuge runs with an interior temperature of about 2600 degrees. The centrifuge is designed and built in our factory. The cells we make will measure 1 inch by 12 inch, and we'll load over 30 at a time into our centrifuge. And we're only going to show one in the movie to illustrate the process, but the output of this small unit will be over 1,000,000 watts each year. Depending on the thickness of the silicon we choose, the distinct possibility exists for us to have an output of about 2,000,000 watts from the same unit. Thinner, less silicon equals faster. We think the centrifuge will cost less than $200,000 once we lock in the design, and our total capex should be less than $400,000. That would be the cost for a complete production line turning out 1 to 2,000,000 watts each year. Here you can see our entire production scheme. You can see a silicon deposit area. You can see our centrifuge. You can see the phosphorus diffusion chamber and the silk screen chamber. Now the phosphorus diffusion chamber really isn't built to scale. That'll be a little bit longer, but we wanted to show it here. And the silk screen chamber is also a little bit longer, but they're simple chambers. The centrifuge and the silicon depositing area are really to scale, and that's really the most important part of our process. We'll get the movie started here. First of all, you see the carbon substrate moves underneath the silicon deposit spot, where a layer or a bead of molten silicon, which hardens up immediately, is deposited onto the graphite. Then the graphite with the silicon on it is moved into the centrifuge, and the centrifuge starts to spin and then heats up. It melts the silicon and spreads the silicon out into a thin layer onto the carbon substrate. You can see the thin layer of silicon spread evenly here. It's no longer a bead. After that happens, it moves into the phosphorus diffusion chamber, where the junction is made, which turns it into an actual solar cell. And then it's moved into a silk screen chamber, where the top electrical contacts are silk screened on, and then they're baked into it. After this, it actually moves on into electrical testing area, and where it's sorted and it'll be assembled into an array. This is a very high efficiency. It's a low cost method. It's USA made, and we really think it can be done. Thank you.